Welcome back, everyone, to IB Physics with Rao for another deep dive into physics. This time, we're going to be building on what we talked about last time with electric fields and forces,
Okay.
and we're going to be taking on electric potential,
All right.
which is a pretty tricky concept. But once you get it, it's really going to unlock a whole new level of understanding about how charges behave.
Yeah, it's kind of like going from seeing the individual trees to understanding the whole forest.
Exactly. Yeah, you start to see the bigger picture.
Yeah.
So for concept one,
Okay.
let's imagine we have a hollow metal sphere, and it's got a positive charge spread across its surface.
Okay.
Now, if you think about that for a second, where would the electric field be strongest? Would it be inside the sphere or outside the sphere? Just take a moment to picture it in your mind.
Okay.
And remember what happens to charges on a conductor.
Okay, so that's a classic question that's designed to test your understanding of how charges behave on conductors.
Right. Okay, here's a hint. Those charges are all repelling each other.
Yeah.
Right? They're trying to get as far away from each other as possible.
Okay.
So where would they end up?
On the surface. So all of those positive charges, they crowd onto the outer surface of the sphere.
Right.
And because they're distributed evenly, their electric fields inside the sphere, they cancel each other out perfectly.
So what does that mean for the electric field inside the sphere?
It means the electric field inside is zero. It's kind of like being inside of a Faraday cage. You're shielded from external electric fields.
Oh.
And this is actually used in real-world applications like protecting sensitive electronic equipment from electromagnetic interference.
Interesting. Okay, yeah, that's super cool.
Yeah.
And this is definitely something that could pop up on your IB exam, so make sure you really understand why the electric field inside a hollow charged sphere is zero.
Yeah.
All right, ready for concept two?
Let's do it.
Okay, picture this. We've got four identical positive charges, and they're at the corners of a square. What would the electric potential be right at the center of that square? Just pause for a second and try to visualize it.
Okay.
Now remember, electric potential is a scalar. So what does that tell us about direction?
It means we don't need to worry about vectors and angles.
No.
We can just calculate the potential due to each charge and just add them up.
Yeah, exactly. It's like adding the prices of four items in your shopping cart.
Right.
Each charge is contributing to the total potential at the center.
Yeah.
And we just sum them up.
Yeah, and because the charges are identical and they're all the same distance from the center, the total potential at the center is simply 4 times the potential from a single charge.
Perfect. Yeah.
Yeah.
And this idea is crucial for understanding how charged particles behave in all sorts of systems. You know, like the arrangement of electrons in an atom or the flow of charge in an electric circuit.
Right.
Now let's get into something a bit more challenging.
Okay.
Concept 3. Imagine we have a graph, and it shows how the electric potential is changing
Okay.
between 2 point charges. Let's call them Q1 and Q2.
Okay.
The challenge here is to figure out the ratio of those charges just by looking at the graph. So take a moment to think about that.
Okay.
What information on that graph could help us determine that ratio?
Graphs are like puzzles in physics. They hold the clues that you need to unlock the answer.
Right.
Yeah.
So here's a hint. Remember that the electric field is the negative gradient or slope of the electric potential.
Right.
So what would a point on the graph where the electric field is zero? What would that look like?
It would be a point where the slope of the graph is 0.
Exactly, that's the key.
Yeah.
If we can find that point on the graph, we know that the electric forces from Q1 and Q2, they're balancing each other out perfectly.
Yes, and from there we can use the distances from that zero field point to each charge, and we can set up an equation using Coulomb's law to solve for the ratio of Q1 to Q2.
It's like a physics detective story where the graph holds the evidence.
I love it.
Yeah, and understanding how to interpret these graphs is a superpower in physics.
For sure.
Okay, you ready to move on to concept 4?
Absolutely. What do we have?
This time, we're in a uniform electric field,
Okay.
and we have 2 points X and Y that are within that field.
Okay.
What we need to figure out is the change in electric potential between those 2 points.
Right.
So imagine those points in your mind,
Okay.
and remember what you know about electric field lines and equipotential lines.
Okay.
What's the relationship between them?
Equipotential lines connect points of equal potential, and they always cross electric field lines at right angles.
Right, they're perpendicular.
Yeah,
And that's the key to figuring out the change in potential between X and Y.
right.
It all depends on the component of their separation that's parallel to the electric field lines.
So if we know the strength of the electric field and the distance between X and Y along the direction of the field, we can calculate the change in potential.
Exactly.
Yeah.
And this concept is really helpful because it helps us understand how much energy a charge gains or loses as it moves through an electric field.
Right.
Which is, a really important idea when we're thinking about things like particle accelerators
Yeah.
or designing circuits.
It's everywhere.
Yeah, it pops up everywhere.
For sure.
Okay, so
Uh-huh.
maybe we should take a little break and
Yeah, let's take a break and come back to this.
come back for some more.
Yeah, sounds good.
Okay. Let's see if you can crack this one.
Yeah.
We've got 4 charges, and they're all at the corners of a square.
Okay.
3 of the charges are positive, and they have a magnitude of Q. But the 4th charge is a mystery. We'll call it Q dash.
All right.
We know the total electric potential at the center of the square is 10kQd, where IOD is the diagonal length of the square.
Okay.
Can we figure out the magnitude of that mystery charge, Q dash?
Absolutely. It's like a detective story, but with charges instead of suspects.
Right.
Yeah.
So remember, we can calculate the potential due to each charge individually and then add them all up to get the total potential at the center.
Right. And because the charges are at the corners of a square, we can use a bit of geometry and the Pythagorean theorem to figure out the distance from each corner to the center.
Exactly. And once we have those distances, we can set up an equation using the formula for electric potential and solve for Q dash.
Yeah. After a bit of algebra, we find that Q dash is equal to 2Q. So the mystery charge has twice the magnitude of the other 3.
See, it's just like a puzzle, all the pieces fit together.
Yeah, I love it.
Okay, now let's switch gears and tackle concept 6.
Okay.
This one involves a bit of graph interpretation.
All right.
We've got an isolated hollow metal sphere that's carrying a positive charge.
Okay.
And we have 4 graphs that are showing how the electric potential V is changing with distance x from the center of the sphere.
Okay.
So the challenge here is to pick the correct graph.
Okay. This one tests your conceptual understanding of electric potential, particularly inside a conductor.
Right, so remember what we talked about earlier regarding the electric field inside a hollow conducting sphere? What was special about it?
The electric field inside is 0, right? And that has a direct implication for the electric potential.
Exactly. If the electric field is 0, the potential has to be constant throughout that region.
So we can immediately rule out any graphs that show a changing potential inside the sphere.
Exactly. Now, for points outside the sphere, we know that the potential decreases as we move further away following the inverse square law.
So the correct graph will show a flat line for the potential inside the sphere and a curve that decreases with distance outside the sphere.
Perfect. You nailed it.
Yes.
Now, for our final concept 7, we have a positively charged sphere, and it's surrounded by dotted lines that are representing equipotential lines.
Okay.
We're going to be moving a small point charge closer to the sphere along 3 different paths, labeled X, Y, and Z.
Right.
So the question is, what's the correct relationship between these work values?
This one really gets to the heart of how work and potential energy are related in electric fields.
Right. Yeah. So remember this crucial point. No work is done when you're moving a charge along an equipotential line.
Yeah, it's like walking along a flat path on a hill. Your gravitational potential energy doesn't change.
Right. So any part of the paths that are following those dotted equipotential lines, those aren't going to contribute to the work done.
So the work done depends on the change in potential and the distance traveled perpendicular to the equipotential lines.
Exactly. So take a look at path X.
Okay.
What do you notice about it compared to the other paths?
Path X involves the longest distance traveled, and a significant portion of that distance is perpendicular to those equipotential lines.
So what can we say about LubEx compared to Y and W's?
WX, the work done along path X, will be the greatest.
Good. Now compare paths Y and Z.
Okay.
What do you see?
They both start and end on the same equipotential lines, so the change in potential is the same for both of them.
Right. And what about the distance traveled perpendicular to the equipotential lines?
They both travel roughly the same perpendicular distance.
So what does that tell us about the work done along those paths?
The work done along paths Y and Z will be approximately equal.
You got it. So the correct relationship is WX is greater than Y, which is approximately equal to WIZ.
Perfect. This concept is really about understanding that equipotential lines are like shortcuts in an electric field.
You can avoid doing extra work by choosing a path that stays as close as possible to those equipotential lines.
It's a powerful idea that can really help you simplify complex problems and get to the heart of the physics.
Yeah, it's like finding the path of least resistance, but in an electric field.
Exactly.
Speaking of paths, let's get to our last concept for today. Concept 8. We've got a graph showing the electric potential V as a function of distance r from a positive point charge, Q. How can we use this graph to figure out the electric field?
This one takes us back to the fundamental relationship between electric potential and electric field.
Right, remember the electric field tells us the force per unit charge.
Right.
And the potential tells us the potential energy per unit charge.
Yeah.
So how do we connect those two ideas using the graph?
The key is understanding that the electric field is the negative gradient or slope of the potential graph.
Okay.
So the steeper the slope of the curve at a particular point, the stronger the electric field at that distance from the charge.
So if we see a steep drop in potential on the graph, that means a strong electric field, and a gentle slope means a weaker field.
Exactly. And because it's a negative gradient, the direction of the electric field is opposite to the direction of increasing potential.
Okay.
So if the potential is decreasing as we move away from the charge, the electric field points outward away from the charge.
This concept really highlights how powerful graphs can be in physics. They give us a visual way to understand the relationship between different quantities and extract valuable information.
Absolutely. Graphs are essential tools for analyzing and interpreting data in physics.
All right, so that wraps up our deep dive into electric potential. We covered a lot of ground today, from the behavior of charges inside conductors to the relationship between potential and work, and even how to interpret graphs to understand electric fields.
I hope this session has helped you develop a deeper understanding of this crucial topic in electrostatics.
Yeah, and remember, the best way to solidify your understanding is to put these concepts into practice. So be sure to join the WhatsApp group for this podcast. I'll be posting a challenging question paper there for you to try.
And don't hesitate to reach out with any questions you might have.
That's it for today. Thanks for joining us on this electrifying journey through the world of electric potential. We'll see you on our next deep dive.